Hello and welcome to my videos, and we are learning some cryptography concepts and some algorithms, and we are exploring this cryptography library in Python. And in last video we talked about AEAD, that is authenticated encryption. Today we are going to learn about asymmetric algorithms, and we are going to talk about ECC, that is elliptical curve cryptography. So in asymmetric algorithm section you can see ED25519 signing and key exchange, and ED448. So these keys are same: ED448 signing and X448 key exchange, and then elliptical curve cryptography, RSA, then Diffie Hellman key exchange. So there is a elliptical curve Diffie Hellman key exchange is also there. That is also we are going to check. But before that, let's understand what is elliptical curve cryptography. We all know about public key, private key cryptography. So in elliptical curve cryptography, the basis of the creating this key is elliptical curve in a plane of elliptical curve. So there are two branches in mathematics. One is discrete logarithmic algorithms, and another are elliptical curves. Okay, so in this part, what happens is, so there are again private keys and public keys are created, ECC keys, and there is a generator point. So we are not going to discuss the low level implementation. If you want to look at how this elliptical curve looks like, then you can Google it. So that is not in the scope of this video to go deep and understand what is ECC. This elliptical curve cryptography algorithms, so we have signing algorithm, ECDCA, and we also have key exchange algorithms. Okay, so but what are the advantages or disadvantages of choosing ECC versus traditional RSA algorithms, which are already there in the market? So let's understand. So as I mentioned, the basis is a mathematical model of elliptical curves, versus RSA is primarily based on prime factorization approach. That is, I have mentioned in one of my videos that extended Euclidean's factorization algorithm is used to factorize this big prime number to find these co-primes. Okay, ECC gives significant bandwidth saving. So bandwidth saving is one of the advantage. RSA provides much lesser bandwidth savings than ECC. So RSA keys are, if you have seen these RSA keys that we generate when we add this, if you have used GitHub or where we actually, or SSH keys for that matter, you must have seen that key length is very huge. We copy that key length in server side so that client server can make connection. SSH .sh, if you look at on your local machine, then you would understand the key length is very lengthy. And encryption process, ECC is very slow compared to RSA. It performs encryption and decryption. It is slower compared to RSA, but ECC is much safer than RSA and is currently in the process of adapting. So ECC is already in the market, and I personally have used ECC for one of my client, and RSA is heading towards end of its tenure. So it's good to use ECC, and we are not even discussing about RSA. We are directly going to discuss about ECC. Okay, here you can see security. If you want 80 bits of security, then RSA key length you need is 1024, but ECC key length is required in between 160 to 223. Okay, so you can see the significant drop in size. That's the reason there is significant bandwidth saving. You can see here. So similarly, for 256-bit security, we need 512 plus ECC key length. Okay. Yeah, one more thing is we have to talk about. This is safecurves.cr.yp.to. This website, you can just Google safe curves. You will be redirected to this site. I will mention this site in our description section also. What this site tell you? So this site is basically hosted by Daniel J. Bernstein. What exactly are the safe curves? So the safe curves are the curves which are very safe to use, but safety from what angle? So here you can find it out. So each of these, so these are the standards for selecting curves for elliptical curve cryptography, that is ECC, and each of these standard tries to ensure that ECC, discrete logarithmic problem, is difficult. So problem should be difficult to solve, so that only it will be qualified for cryptography. ECDLP is a problem of finding ECC user's secret key given the user's public key. Okay, So unfortunately, there is a gap between ECDLP difficulty and ECC security, right? So there is a difficulty problem and security problem, right? So none of these standard do a good job for ensuring ECC security. So we have two objectives here. The ECDLP difficulty should be sufficiently large. That is, it should be, we talked about entropy, right? But at the same time, it should provide ECC security. It should be good enough. Okay. So there are many attacks to break real world ECC without solving ECDLP. The core problem is that if you implement the standard curves, chances are you are doing it wrong. So that's the reason. This safety means that you will face this problem. Your implementation may produce incorrect results for same rare curve points, or it may leak secret data through these many problems. So that's the reason. What they are suggesting is to use from this curve. So if the curve is safe, so this curve 2559 and ED, ED448 Goldilocks. So these two curves are here, ED 2559 and 448. So difference between two is, I guess, key length. Let's understand. So yeah, so there are two. So basically, this is not an encryption. Okay, this is a key exchange, and this is the example. Let me copy, paste, and I will explain this to you. So this is about X2559, and this is key exchange problem. This is like Diffie Hellman key exchange, where two parties are agreeing upon one symmetric key, and that symmetric key is encrypted and exchanged. So let's understand how this key is exchanged. So first of all, first party, so we create private key. In real handshake, the peer public key will be received. So let's assume that this peer public key we are receiving from another party. Okay, this key we are receiving from another party. Then this exchange happens, private key dot exchange this peer public key, and we get the shared key. Okay, and from the shared key we derive final key. This is derived key. So actually speaking, this derived key should be the one that we should be printing. Okay, so basically this shared key here is common across. So these two are not going to same. Okay, so what we should be doing is, for next communication we would be creating new private key, and there will be again we will be receive public key, different public key. So for better explanation, you can watch our hybrid cryptography video that I have the link I have mentioned in our first video of this series, and I will mention that one again. So there you will understand that how this public key, private key, that is asymmetric keys, are used to exchange your original key, the shared key. Okay, so this HKDF, this key derivation function, is used to derive our key. So this function basically makes sure of it adds more randomness and performs some extra work. You can provide salt, but if you are providing salt, then what you need to do is you need to exchange that salt also with your peer, right? So this is how your elliptical curve cryptography works. And there is one more example here. So this is curve 2559. So it uses, I guess, it uses actually 32 byte public key, but internally, let's understand X448. This is even stronger than 2559. Let me run. So in fact, the code is almost same. As you can see, we first generate private key, then we receive this public key from your server. So remember that this key, this particular code dot generate, this you have to look for the library on your client platform. So in my case, I have found that in iOS and Android both have 2559 implementation available. I'm not sure about X448 private key is now available or not, because OpenSSL also just when they started supporting this key exchange, I guess this library has this implementation. I'm not sure about iOS and Android implementation, that you have to check. But whatever client technology you are going to use, you have to see for the library, and it should generate this private key, public key for this algorithm. Okay, and it should also have this HKDF function, where this HKDF is key derivation function, which will be used to derive the key. All right, so this is the derived key which you will be using for next communication. So this derived key will be common for your client and server. So this is like symmetric key. Okay, so yeah, this is about ECC. So in next video we are going to talk about post quantum cryptography. So thanks for watching my video.